This event is sponsored by the SPU Initiative for Individuals with Intellectual and Developmental Disabilities. It's been a part of SPU for the last 10 years, and we're hoping to continue that. And we sponsor events for speakers to come on campus. We also sponsor an autism awareness event in April. So if you've signed up for the list here, the email list, or phone numbers, whatever, we will be contacting you about that as soon as those events get scheduled. We're delighted tonight to have Dr. Anna Arnett with us. Dr. Arnett obtained her Ph.D. at the University of Denver. She's currently an assistant professor of psychiatry and behavioral science at the University of Washington. She's also an attending clinician at Seattle Children's Hospital. Her research examines ADHD, dyslexia, autism, and genetic syndromes, and she's currently completing an NIMH grant investigating neurobiological subtypes of ADHD. Pretty exciting stuff. And so we're very pleased to have her with us tonight to talk about ADHD, and please join me in welcoming Dr. Arnett.
Thank you all for being here tonight, and thanks for having me. How is the volume? Would you rather use the microphone? Yeah. Okay. Is that better? Button down here. Is that better?
Yeah.
Okay, great. That's actually easier on my throat too. Okay, so I'm excited to be here tonight to talk to you all about ADHD, or Attention Deficit Hyperactivity Disorder, and we'll be talking a lot about the brain as well as individual differences among people who have ADHD. So before we get off and talk about the research, I just want to clarify that when I say ADHD tonight, I am talking about all clinical subtypes of ADHD. So some folks call it ADD and drop out the H if the child does not have hyperactivity. The current nomenclature is ADHD, and then we specify predominantly inattentive or predominantly hyperactive, impulsive, or combined. So tonight when I say ADHD, I'm talking about all of those together. The name has actually undergone a lot of change over the last century, really. Initially it was called hyperkinesis or hyperkinetic disorder of childhood. There was really an emphasis on the hyperactivity and impulsivity component. At this point we've shifted and the emphasis is a little bit more on attention. But if I had my druthers, I would call it a disorder of regulation. Maybe one day I will. Maybe I'll be put in charge of that one day. You'll know when it gets changed to that. And the reason I would call it disorder of regulation is because what we see in people with ADHD, children and adults alike, is that they have difficulty regulating or doing self-regulation in a lot of different domains. And as a human being, we are required to regulate ourselves throughout the day. So, for example, we have to regulate our attention. We have to pay attention to the things that we're supposed to pay attention to when we're supposed to pay attention to them. And then, likewise, we have to not pay attention to those things that are irrelevant, those distractors. And that requires some regulation of our attention capacity. We have to regulate our activity level. And that means both sitting still and sitting calmly when necessary, but it also means increasing activation and kind of increasing that energy level when it's appropriate. We have to regulate our impulses. So when you go shopping, you cannot just buy everything that looks good to you. You have to work on a budget. You have to think about and prioritize things. People with ADHD are at much higher risk for substance use disorders for this reason. Impulse control is really challenging. And regulation of emotions. So as a clinician at Seattle Children's, I see a lot of patients almost across the board. The children that we see have difficulties with emotion regulation. They are 0 to 60, these are extreme temper tantrums, and they're experiencing those emotions at that level. And regulating emotions, it's not actually part of the diagnosis right now, but it is a main symptom that we see. Okay. Polyunit disorder of regulation also explains why sometimes kids with ADHD seem like they can focus really well. So for the parents in the room, this picture may look really familiar. Kids with ADHD are often, you sit in front of the TV, you give them a video game to play, and they are focused. They don't hear mom calling them in for dinner. They can't think about that homework assignment they were supposed to do. A lot of parents will say, a smoke alarm could go off in the room and they're not going to hear it. And obviously, that inability to disengage and regulate our attention away from an activity like a video game can be a problem, particularly if there's a fire. Okay, so another concept that I want to introduce before we move into the research is we think about ADHD as an extreme representation or expression of a continuum of behaviors and or a continuum of behaviors that we see in the normal population. So some of you may be here tonight as an armchair psychologist, here to diagnose yourselves or your family member or your child. And the fact is we all have some symptoms of ADHD at some point in our lives. We all forget our keys. We all have difficulty prioritizing at times. We all buy that thing we shouldn't have bought every once in a while. But kids with ADHD fall into that right extreme tail where we've got more severe symptoms on the right there, and they're more frequent, they're more severe, and importantly, they are impairing. So they're getting in the way of everyday functioning. So these kids are not just severe, but they're also experiencing impairment as a result of these symptoms. So that's where those kids fall. On the other end of the spectrum, we have people, it's a small group of people also, who are extremely well-organized and well-regulated, people like Marie Kondo. But most of us, myself included, fall somewhere in that middle range there. Where we have some of these symptoms every once in a while. We have a bad day or a bad morning, but for the most part, we're getting really difficult. Okay, so ADHD has been around, it's been documented, interestingly enough, since the early 1700s. There's some indication in the literature by various medical professionals that they were seeing symptoms of ADHD. And the interesting thing to me is the consistency with which they describe these kids who are having these challenges. Again, the emphasis was much more on the hyperactive part, but there were definitely references to difficulty with attention and persisting through difficult tasks. This cartoon behind me comes from actually a children's book. It was an illustrated children's book written by Heinrich Hoffmann, who was a German psychiatrist. And he wrote this book mostly from the perspective of poor Fidgety Philip's dad. So the title of the book is Fidgety Philip. He wrote it in 1844. And this kiddo is encountering, in this image, he's encountering his arch nemesis, the dinner table. You can see at the top, he's sitting in his chair, and he's rocking back, and then the inevitable happens. He tips over, he pulls everything down on top of him, and his parents are furious. And this scene is so common back in 1844 and today. I mean, there are parents in the audience, you have seen this happen. Dinner is really challenging for kids with ADHD. So that consistency is important in terms of what we're going to talk about next. Another brief history, this is the history of my work. So I started at UCSF, at University of California, San Francisco, before I went to grad school, and I was actually studying autism. And I applied to graduate school, and I stumbled on a guy named Bruce Pennington, who's a really fantastic researcher. He's now retired, but he was a pioneer in the world of neurodevelopmental disorders, and I was lucky enough to get to work with him at the University of Denver. And when I joined his lab, he was studying ADHD. And I didn't know a lot about ADHD at the time, honestly, but I just immediately fell in love with these kids and this disorder. They're super interesting. They're fun, they've got energy, and they are funny. I mean, the stories we would tell about working with these kids were just fantastic. And I used to say, actually, when we would do evaluations and we would talk as a team about kind of the behavioral observations of these kids, I would say the harder we laugh when we're describing these things, the more likely this kid has ADHD. Because they were just so funny, the things that came out of their mouths, the tipping over the chair, it was great. And then I went to Seattle Children's and UW for my clinical internship, and then I ended up in a postdoc in the Bernier lab, and they study autism, so I was back in the autism world again. But I really miss those kids with ADHD, and so I managed to get some grant money, and now I'm working on some research that I'll talk about later. But somewhere in there, somewhere in that timeline, this happened. Oh, I'm just pushing music, but that's good. supposed to be Chariots of Fire. Another familiar scene. Okay, so that was one of my kids when he was only 5 months old. And he had been crawling like that since he was 3 months old, which at the time we thought was awesome. We were like, he's so precocious. All of these muscles, you know. And it wasn't a total surprise because he'd been doing jumping jacks in my womb for like 9 months. We were used to that. And he, as it turned out, 4 or 5 years later, there was no denying that he had ADHD. And I consulted with a lot of people because I was really worried I was over-pathologizing my child. And his teachers were very reassuring that yes, he had ADHD. And having a child with ADHD has been a blessing, one, because I have hours of footage and anecdotes for talks like these, but also because it's given me a lot of empathy for the patients that I work with. And the clinical work that I do and the personal experiences I've had have really informed the research questions that I ask, and the research that I do, I hope, is having the most impact possible on the outcomes for these kids. So some of the challenges with ADHD right now, we actually have a lot of great treatments for ADHD, but some of the challenges are that we do not have a very early diagnosis age. Most kids get diagnosed in early elementary school because the symptoms that we see early on are not very specific. I mean, that kiddo right there was very persistent in the face of challenge. Having a high energy level as a 2-year-old boy does not make you stand out. And so it's really hard right now. We don't have a good way of predicting diagnosis in early infancy. Comorbidity. We do not know how to tell you if your child's also going to have learning disorders or anxiety or depression. We don't know what's going to happen over time. About half of kids actually remit around adolescence and don't have symptoms that persist into adulthood. But then there are plenty of people who do persist into adulthood, and we really cannot predict that right now. And treatment. So again, we have some great treatments, but there are a ton of treatments out there, a ton of pharmacological treatments and behavioral treatments. And it's really trial and error for clinicians right now. A lot of them work, but we don't necessarily know the optimal dosage or optimal kind of form of that medication or that behavioral treatment for each child. And so it really depends on your clinician how close you get to that. And one reason for all of these challenges is the amount of heterogeneity in the group of kids with ADHD. And heterogeneity means individual differences, just a lot of variability among these individuals in terms of symptoms and comorbidity and development and treatment response. It's really hard to get a handle on a predictor for a group that has so many different outcomes and probably causes for their disorder. So the goal of my research, and some other research that's going on right now, is to parse this heterogeneity, which means break it down, figure out which individual differences are most important, are going to predict these outcomes, and are most closely related to causes that we can then link to treatments. In this pyramid, at the very top, we have behavior. So we can break it down by behavioral symptoms. And that has really been the effort that you've seen in the diagnostic manuals and kind of underlies that confusion around, is it ADD, is it ADHD? So we do, from a clinical perspective, specify it's predominantly inattentive, or it's predominantly hyperactive impulsive, or it's combined. And initially when this came out in the 80s, we thought this is it, we've figured it out, there's got to be a different cause for the inattentive kids and that's separate from the hyperactive kids, and they'll probably respond to treatments differently too. Turns out not. And one reason for that is that these subtypes are really unstable. So this is a figure from a study that came out in the 2000s. Some of my colleagues in Colorado wrote this paper. And this graph is a little bit confusing, but basically what this is showing is that there's a ton of change in subtype classification over time. So on the y-axis, the vertical axis here, we have the percent of kids who meet criteria for a different subtype as compared to the first subtype that they were given when they first came in. And then on the x-axis, we have the year of the assessment. So over the course of 8 years, if you look at that, these dark circles here are kids who were initially diagnosed with the hyperactive impulsive subtype. And by year 8, more than 80% of those kids met criteria for a different disorder, or a different subtype. The inattentive subtype, there's a little bit less variability, but again, even at its peak, we're seeing about 50% of kids meet criteria for a different subtype. And then the combined subtype, which is the most stable, even by year 8, 40% meet criteria for a different subtype. So what all this means is that while these subtypes may be helpful in terms of informing what's the child's most challenging behavior in this moment, it's probably not linked to the cause or going to be predictive of outcomes because it's so unstable. So the next level that we can try to parse heterogeneity is at sort of the intersection of behavior and brain, and that is what I call cognition or cognitive profiles. So when we measure cognition, if I sit down with a child at a table and give them an IQ test, or we do some processing speed tasks or some memory tasks, it's still considered behavior because we're measuring it more subjectively. It's not quite at the brain, but it's a little bit closer to what we think is happening in the brain than, say, inattention versus hyperactivity. So there are a lot of different types of cognition that we measure that we think are related to ADHD. The first is processing speed. Processing speed is the ability to do something, to kind of make sense of simple information and do something with it as quickly as possible. And kids with ADHD have slow processing speed. Not across the board, because again, there's individual differences, there's heterogeneity, but this finding is one of the most consistent findings out there, that their processing speed is slow. The problem is processing speed is also slow in kids who have dyslexia and autism and other neurodevelopmental disorders, so it's not a very specific predictor of ADHD. Verbal working memory is another type of cognition that we measure, and so it's something like if I read a bunch of numbers to you and you would have to say them back to me backwards. Spatial working memory, similarly, I could show you a map of the city and have you try to reproduce a part of it. After I took it away, you'd have to remember and to do something with it. Inhibition, at one point it was thought that inhibition was like the answer to ADHD, that all kids had inhibition problems and that was going to explain all the variance in their ADHD symptoms. But it has turned out that, as you know, you're going to hear me say over and over, there's heterogeneity, and so not all kids with ADHD have inhibitory problems, at least as far as we measure them cognitively. In this task here, this is a version of the Stroop task, which you may be familiar with, and what we ask people to do is say the color of the ink and not read the color name, and it's really hard to do because you are inhibiting a previously learned behavior, which is reading. And even kids, school-age kids, have overlearned reading to the point that it's really hard to stop themselves from saying the color, or from reading the word. And then the last one that I'll talk about tonight anyway is reaction time variability. So we sit kids down in front of a computer and give them a pretty simple task, and they have to press X when an X pops up and O when an O pops up. We will see that they are not only, kids with ADHD are not only slower in general, they're more variable. So they may take a while on this one time and be much faster on another one, and they're just kind of all over the map, whereas kids who do not have ADHD tend to be a lot more consistent in their reaction times. So we can measure a child's performance on all of these domains, for example, and then plot it in what I would call a cognitive profile. So on the y-axis here we have the score, higher being better, and then on the x-axis we have each of those cognitive abilities that I was just talking about. And so this is just made up data, but this child, for example, has kind of low average working memory, decent processing speed, average inhibition, real deficit in spatial working memory, and the reaction time variability is actually okay. And the problem with heterogeneity is that when we have looked at all of these different domains and tried to use these sorts of problems or abilities to predict behavior in terms of ADHD severity, we only are able to explain about 50% of the variance. So it's not explaining everything, it's not predicting everything. And so one thought we've had is, well, maybe it's different combinations of these profiles that are explaining variance or behavioral variance in different kids. So this comes from data from the Colorado Learning Disabilities Research Center. It's a huge twin sample, and Eric Wilcott is the PI over there. He's a colleague of mine, and this is data that I worked with in graduate school. And what we did here is we took a bunch of data from these kids, about 3,000 kids or 1,500 twin pairs, and we sort of plugged it into this black box, this statistical algorithm, and asked the computer, how many profiles are there? What are the most common profiles? How many are there? And who falls into each group? And what the computer told us is that there were about 4 profiles that were most commonly seen. Ignore the fact that there are different colors right now. I'll talk about that in a second. But there's this first one that's about high average, so everything's pretty consistently above average here. There's the average group, again, a fairly stable profile. There's this group that has inhibition, and SDRT stands for standard deviation of reaction time, so that's reaction time variability. And this group had lower inhibition and much lower, or meaning more variable reaction time. And then this last group here really has if you can see this red triangle, they have a deficit in spatial working memory. So that was pretty cool. We were pretty excited to see these different profiles, and actually these profiles line up with another group at OHSU who has done very similar work. But the problem is that, so these white lines are actually kids who don't have ADHD, and the red triangles and lines are kids who do. And so what's interesting, and this is true of the group at OHSU, what they found as well, is that these profiles are not specific to ADHD. These are population cognitive profiles. They probably are more related to evolution and kind of this Darwin effect of it's really helpful to have a bunch of people with different strengths and weaknesses in our society so that we all work together to get things done and don't have all the same interests and strengths. And so the only thing that we really see is that kids with ADHD tend to do a little bit worse on most of the domains than kids without ADHD. And then there is a much stronger spatial working memory deficit here, but we don't totally know a lot about that at this point. So it's interesting, it's work that we're continuing to do, but it's probably not going to explain as much as we had hoped. So I'm going to skip over the brain for a second, because that'll be kind of what I focus on at the end of the talk. And talk about this layer here, which is the ribbon. It looks like candy, but it's supposed to be DNA, the helix. There is a ton of heterogeneity and genetics too, just to give you the bottom line right up front. We have been looking for the ADHD gene for a long time. We really haven't found it. There are certainly some genes that seem to be more related to ADHD, genes that are related to dopamine transmission and production, for example. But the genes that we have found explain very little variance in the behavior. And up until recently, there weren't really any genes that were reliably being found in research that was, when we try to replicate research. So this figure is kind of confusing, but it comes from a recent study. It was a genome-wide association study, GWAS. And basically what these people, this research team did is they took a ton of people, some of whom had ADHD, some of whom didn't, and they looked at their whole genome. They looked at all their DNA, all their genes, and they compared the people who had ADHD to those who didn't, and tried to find some genes or certain expressions of genes that seemed more related to ADHD. So on the x-axis here we have the chromosome, and then on the y-axis we have the significance level, and they're correcting for multiple comparisons here, which is why it's so high. And essentially what we see is that each of these little yellow lines, these peaks here, represents a gene that passed the threshold for significance in terms of being related to ADHD. So this is a different location on the genome that seemed to be related to ADHD. So in this study, on the one hand, it was great news that we actually found some. On the other hand, in this study alone, there are 12 genes that are contributing to ADHD, and altogether they only explained about 20% of the variance in ADHD. So it's really low, and really what we think is happening is that there's a lot of additive genetic risk, there's interactive genetic risk, so genes can influence the way another gene is expressed, and there is gene by environment interactions, which means that the environment can influence the way your genes are expressed. And this is one of the ways that we explain the fact that even identical twins who have the same DNA can turn out to look differently and behave differently and have different personalities, because there's a lot of variability in the way your genes are expressed. So that brings us to the crux of my talk, the brain. I think this is a good place to go in terms of trying to explain heterogeneity. I think all of these places are good places to go, but I'm excited about the brain research because with the genes there are countless permutations of possible causes for ADHD. And so it's great work, it's also going to be exhausting work, and it's going to take a really, really long time to find any sort of biomarkers there or understand exactly which combinations of genes are going to explain ADHD. And the brain, on the other hand, is being expressed as a result in part of our genetic expression, and so it's kind of a proxy for genetic expression that gets rid of all that confusion of which genes are adding up to what. So we have taken the approach of trying to parse heterogeneity using brain data. This is a slide that just goes over what I just said. So we've got behavior on this side, so there are a lot of different behavioral differences. This is heterogeneity. When we look at the brain, we hope that what we can do is identify some markers of brain activity that will then predict these different subgroups, which could have meaning at the level of predicting symptom severity, comorbidity, development, and most importantly, treatment response. We know a lot about the brain in terms of how it's related to ADHD. Up until this point, most people have looked at brain differences at the group level. They've taken this bird's eye view of how do all these kids with ADHD compare to all these kids who do not have ADHD in terms of their brain. So we haven't really addressed the heterogeneity thing all that well yet. But there are some interesting findings. The frontal lobe is a structure in the front of your brain that we think is highly involved in sort of complex behaviors, executive functioning like organization, planning, regulation of your emotions and your impulses. And so it's not a surprise that that seems to be implicated in ADHD. And what we see is that in general, the frontal lobe in kids with ADHD is smaller and it's less well connected. There is an interesting finding where in the prefrontal cortex, there are two sides to your brain, and when in infancy, for most people, the left prefrontal cortex is larger, but then by adulthood, it's actually the right prefrontal cortex that has taken over and become larger. And with kids or individuals with ADHD, we don't necessarily see that change. So there are some really interesting findings there with implications. But we also see differences in the cerebellum, which has been implicated in gross motor and balance, as well as the limbic system, which is involved in emotions. And it's really hard to say how much of this is a result of experience versus the underlying cause. And most importantly, we're actually starting to move away from looking at structures and just the size of things, and instead focus on how these areas of the brain communicate with one another. So that communication piece and how, for example, the frontal lobe might actually inhibit that emotion center seems to be more important than just how big are various centers of the brain. So one way that we can look at these connections and at sort of more functional level of the brain is using EEG, which stands for electroencephalogram, and we use EEG to measure electrical activity in the brain. And I'll show you, we put on this funny hat on our kids. Obviously they love it. Big smiles. And that hat has 100, we use a dense array, which means it has 128 electrodes. Those little buttons on the hat are electrodes. Inside there's a little sponge and there's a little metal electrode. And what it does is it measures that electrical activity in the brain. There's not a lot of electricity in the brain. We can like plug an iPhone into your ear and charge it up by any means, but there's enough with every thought and impulse you have. I mean, your brain's just constantly, that's how it works. So there's electrical energy in there. And our system can pick up on, it's very sensitive, it can pick up on that electrical energy. And so what we see is that each of these lines here corresponds to one of those little electrodes, and we see this just continuous charge happening here. Up is positive, down is negative, and this is over time. And that's what the computer produces for us, and then we go in and try to make sense of it. Oops. Okay. So this is a neuron, and just to help you understand where that electrical impulse is coming from, this is the cell body for a neuron in your brain, and then this is the end of it. And what happens is two neurons connect. The terminal connects to a soma, or the cell body gets close to it, and they send this chemical signal, an neurotransmitter, to one another. And basically what happens is that once that chemical signal reaches this cell body, it can start this chain reaction that causes an electrical impulse to travel through the neuron here. And when enough neurons are excited at the same time and lined up together, then that's when we see that electrical charge make it all the way to the scalp at a level that we can measure it. Now, this signal is a little bit messy, right? But what we do is we use another statistical approach called a Fourier transform to break it down into brainwaves that are actually more regular. So here's a slow brainwave up here, maybe, I mean these are just examples, but like maybe it's a delta wave, and then as the peaks and troughs become more frequent in a short amount of time, for example, this could be a beta or a gamma wave, we call it faster. So it goes from slower frequency to faster. And we think that these different frequencies have meaning. Prior research has shown that, for example, the alpha waves, which are kind of in the middle, are a little bit of a faster frequency, that increases with age and seems to be a marker of development, particularly in the parietal area. And in contrast, some of these slower waves, like the delta and the theta waves, they tend to decrease as people develop. So this is a heat map from one of our research subjects. So this is the scalp, and here's the nose. I mean, they just kind of, our computer kind of puts this schematic on here. This is not really his nose. But here's a nose and some ears. And this is kind of the distribution of that signal around his scalp. And if you can imagine this outer part kind of curving around under the ears and behind the head there. And this is a heat wave map of the strength of the alpha signal, so 10 hertz, with red being stronger and these cooler colors being less strong or weaker. And this kid has a really strong alpha peak in the parietal region. Another way to look at this is to look at the distribution of the strength of the signal right here in the middle of that area. So this is power over here, and then this is frequency. It was slower, going towards faster. And this is that alpha peak right here. It's really clear. Here's another kid. This is another boy, about 10 or 11 years old. They were both boys, 10 or 11 years old. They have very similar intellectual levels. Both have ADHD. We've done our research. And this child has a very different heat map of the alpha power. So there's no alpha peak here in the parietal range like there was with his counterpart. And you can see that again in this distribution here. It's more of a linear change, and we're just not seeing that alpha peak as we did with the other child. Now we're in the beginning of this research, so as a researcher you really try not to make too much of differences between two kids, for example. But some of the things that we're finding seem to be pretty consistent with some other literature. So for example, this, there we go. So this kid over here, the first one we looked at was the alpha peak, has a lot more disruptive behaviors and oppositionality, and he has a learning disorder. This kid over here, much more even-keeled and pretty just like stable, average cognition across the board in all the ways we tested him. Some oppositionality, and clearly does have ADHD, but at the face of it, there's not, you wouldn't necessarily see many differences between these kids. They're both 10 or 11-year-old boys with ADHD who are going to school and functioning, but struggling a little bit with the ADHD symptoms. Here's a figure from another study that did something similar. They also used EEG with kids with and without ADHD, and this study really illustrates the importance of breaking things down and trying to parse this heterogeneity. So there's this left column here is the control group, just average across all the control kids. And this column right here is all the ADHD kids. And so if you just compare these two columns, you kind of zero in, and then, the rows here are, the top is total power, but this is delta power, theta power, alpha power, beta power, so we're going from slower to faster, going down. So if you look at just these first two columns, you're going to zero in on the differences in theta in particular. There's a much stronger theta power among these kids with ADHD. And that would be the story that has been told, right? These are the group differences, so theta power must mean ADHD, right? Well, actually what this group did is they fed their data into the same black box that I fed all that cognitive data into, and they asked the computer, hey, how many groups are there? Who belongs to each group, and what do they look like? And the computer told them there are about 3 groups. There is this cluster 1, cluster 2, cluster 3. And if we look, for example, at alpha, cluster 1 seems to be differentiated particularly because of high levels of alpha right here in the parietal and occipital area. And then cluster 3 is very different at the beta level. They have much stronger beta power. And this one really strikes me because look at the average ADHD. I mean, this group is so different even from the average ADHD, and there were no differences between average ADHD and average controls. And so this would have been totally missed. So this is really cool work and has kind of inspired a lot of what we're doing now. This is another more recent study that did the same thing. Again, they took kids with and without ADHD, and they tried to identify groups, statistical groups, and they found actually a group that had a peak in basically each of these frequencies. So this group has relatively strong delta power in the parietal region compared to all the other groups. This group is characterized by strong theta, alpha, and then the beta group. And similarly to what we're seeing in our early work right now, this paper and the one that I just showed you, one of the strongest findings they had was that there were much more disruptive and oppositional and conduct problems among the groups that had strong high frequency, like alpha and beta power, particularly in that parietal region. But not many differences in terms of intelligence, and no one has really done longitudinal research to say, well, what does this predict in terms of long-term outcomes or treatment response? Okay, so let's take a little break. I'm going to show you something. Some of you psychology students in the room may have seen this before, so just play along. We're going to do a little test of selective attention.
Test of selective attention.
So basically, count how many times the players wearing white pass the basketball.
How many passes did you count? The correct answer is 15 passes. But did you see the gorilla?
It's hard to believe if you didn't see it.
didn't see it the first time.
So this is not a litmus test for ADHD. Most people don't see the gorilla. That's why this is so compelling. And that's because our brains are really good, most of our brains are really good at focusing on the task and ignoring irrelevant stimuli. If you saw the gorilla, that does not mean that you have ADHD. I actually don't even know if there's a correlation between this video and ADHD, but it's a great example of the power of our brains to really zero in on a task at the exclusion of other stimuli, particularly when those stimuli are not like threatening or all that important. In this case, if you were in the room, the gorilla may have felt more threatening, but in the video sense, it really didn't stick out to you. Okay. So there are a couple of different ways that we can think about how our brains regulate things like tasks versus distractors in the environment. And the first is when we see something, or when there's something in our environment, like something visual or a sound that pops up, we have to recognize that sound in the first place, right? That immediate sensory processing is really important. And so it's possible that people with ADHD have difficulty with that initial sensory processing. Maybe they overprocess, they hear and see everything going on in their environment, or maybe they're less tuned into things in their environment and their brain is not processing it at the level that they need it to. And in that part of the process, of the sensory process, we call kind of the bottom up. So from the basic auditory or occipital cortex up. The next level is the executive level. So what do we do with that information? Once that sensory thing has been recognized, what does our brain do with it? How does it regulate it? If you have to plan, you have to do something, you have to push a button in response to that, and there's some planning involved. If you have to ignore it, then there's some inhibition or suppression involved. And that we would think of more as sort of top down, so like the frontal lobe down. So the frontal lobe may be regulating some of that sensory input. So when we look at our EEG data, there's actually another way that we can look at it. In addition to just breaking down those frequencies, we can actually look at a very finite point in time that is locked to a stimulus. And this is just a schematic of what this might look like. So if we kind of amplify this out, first we would clean it up. There's a whole bunch of stuff you do with this data before you can look at it and it looks this clean. But if we amplify it, and this red line is something happening in the environment. For example, a sound, like a bell ringing or something. And by the way, this is called an ERP, or an event-related potential, or some people call it evoked potential. So there are different components, we call them, in this signal, this ERP. And these early ones here are examples of bottom-up, really sensory processing that happening immediately. On the bottom here, we usually measure in milliseconds, so that's how quickly this is happening. And then there's a later peak. We often see a peak 3 that represents what your brain is then doing with that information. And then there's this sort of later time where it's sometimes involved in like encoding. If you're learning a new language, then we expect that is occurring later. So in our study right now, we do a task called the irrelevant probe task. And what the kids do is they put on that hat and they sit in front of a computer and they're given a little button box. And they are told, you're going to see some colored rectangles on the screen. And when you see a blue one, press the right button. If you see any other color, press the left button. Press it as quickly as you can. And oh, by the way, in between every other one, you're going to see something that's totally, that's just kind of random. Just ignore it. And we call those probes, irrelevant probes. They're not relevant to the task. They're just coming up in between. Another word for them would be a distractor, but we don't say that to the kids because that kind of gives it away. So some of these probes look like this. The majority of them do, and then every once in a while we flip it around, so it looks a little bit different, but not that different. And then every once in a while something totally random comes up, like a kind of a line drawing of an animal or a car. These are not our exact stimuli, but they're pretty close. And they do that task for about 7 minutes with a couple of breaks in between, and they do surprisingly well. These kids actually enjoy it. It tends to be their favorite part of the day, and their accuracy is pretty great too. And then we give them another version of the same task, which we call the hard irrelevant probe task. And in this one, it's actually more of an NDAC, if anybody's heard of that. And it's more like a working memory task. So instead of just pressing one button for one color and another button for another, this time they have to keep track of the colors. And with every rectangle, they're thinking back. So if this one comes up, they're thinking back to that last rectangle they saw, and they're thinking, was that the same color as this current one, or is it different? And if it's different, they press left, and if it's same, they press the right. And so they're constantly updating their working memory to do this task. And then again, we have these relevant probes in between. And the idea behind this task is to get a sense of how much the task load, the difficulty of the task, impacts what their brain does with it. And at the more basic level, we just want to know, is this child's brain reacting more to the task stimuli or the distractor stimuli? And if they're reacting more to the distractor stimuli, how do they deal with that? So this is the whole group that we have so far. This is about 18 kids, I think, in this data. Okay, so this is one of those early components showing that after a task stimuli, so this is part of the task that they're doing, they have this initial response that recognizes that there's something going on the screen. And the easy and the hard tasks are about the same, but there's a little bit of a peak on the hard, and the reason for that is that they're working a little bit harder. They're allocating a little bit more attention capacity to processing in that harder situation. And then later on, when they actually have to do something with it, they have to respond, you see a really strong peak. They're really using more energy to do that. And that's what we would expect. So as a whole, the kids are actually doing what we would expect out of any kids on this task. But when we break it down into individuals, this looks a lot more messy because when you have individuals, it is more messy. That's just the way it is. And things get speeded up a little bit. But trust me, it's still meaningful. So when we compare two individuals, we see a very different story. So this kid, again, is processing the hard task. So when he sees that task stimuli during the hard situation, he's working a little bit harder for it initially on, and then also working harder for it there in the more executive part. This child, on the other hand, doesn't seem to be rising to the occasion for the hard task, either early on or later. And these kids are the same ones that I showed you earlier, just for consistency's sake. So this is the child who has more oppositional behaviors and disruptive behaviors, and this is the child who's pretty even keel, about average intelligence. But guess what? This kid did a lot worse on these tasks than this one, or on the hard task anyway. They did about the same on the easy, but worse on the hard. Now let's look at how they respond to the irrelevant probe, the irrelevant distractor stimuli. This is the whole group, again, kind of a bird's eye view. And we see this sort of decrement in the hard signal, or in the response to this in the hard signal, and that's again what we would expect. So there are fewer resources in that hard task because they're working so hard to do the task. There are fewer resources to process that irrelevant stimuli, so that's great. And then later on, with the executive component, it's about equal, and that's fine too, because there may be some effort into sort of suppressing whatever they are recognizing. But again, we're going to break it down at the individual level, and in this early sensory part, this kiddo is processing both about the same, maybe the easy one a little bit slower. But this child is allocating a ton of resources to processing these irrelevant probes. He's not discriminating very well. I don't have this graph up here, but when you look at the strength of this response to the irrelevant probe as well as the task stimuli, it's about the same, and he really should be kind of decreasing that effort. In the easy task, however, he's able to kind of decrease his response to this, and that may in some ways be kind of a top-down effect or an inhibition effect that he's able to do in that context. And then here, again, a lot of attention and effort being paid to dealing with this irrelevant probe. It's not relevant to the task he's supposed to be doing. And then this child actually does seem to have less effort later on, maybe because he dealt with it there. I mean, it's hard to make too much sense of a single ERP. This is not clinically diagnostic, and this is the work that we're doing. We're at the very, we have another 60 kids with ADHD at least to see, and then hopefully we'll get to a point where we can kind of break it down into those clusters and say, how do these subgroups map onto their behavioral profiles and their response to medication and all the other things that we're measuring, learning disabilities, things like that. So, with that in mind, the main question, this is all kind of fun. The EEG is fun, it's fun to think about the brain, but the main question that we really want to answer is how does this relate in the long run to interventions? How are we going to help these kids and these families affected by ADHD? And we call that translational research. How do we go from the brain information and even the cognitive information to predicting what kind of treatment and at what dosage kids are going to respond best? And so again, we were always really thinking about these 4 factors when we do this research. There are a couple of studies going on right now that are addressing this. So this is the study that I was just talking about. So we're studying 7 to 11-year-olds. This is the team study where they're really looking very closely at kids' responses to medication, particularly when they go off of medication. And I have handouts for these if anybody is interested or knows people who may be interested. That one, again, is looking at 7 to 11-year-olds. The Achilles study has not started up yet, but is another treatment study where we're looking at medication responses. And then this FNIR study is a really cool, again, hasn't gotten started yet, but we're in the early process of designing it. And the researcher there does, she looks at like the chemical response to the medication in vivo, like in real life. It's a very cool technology that I don't actually know a ton about, but she's able to put these kids in a scanner and look at how their brain chemistry changes when they're doing a task, when they're on medication versus off. And so that is super promising, and we are cross-recruiting between my study and this one so that we can see how that relates to the ERP data as well. So I just want to say thank you. Tara is the person who got me here tonight. So this is Tara Rudder, a psychology graduate student here and a student in my lab. Candace here is another student over at UW. These are my undergraduate phenoms. And Ray Bernier is one of my mentors. And the CHDD is the building where I work in this wonderful center that really supports our research. And then the CLDRC is that Colorado group that provided the data for the cognitive work. Questions? I'm happy to take questions.
What other kind of like resources or any like authors that you trust or like websites that you could offer for parents or family members?
Yeah, you mentioned the people who are leaving, we will be able to post a video of the presentation. So should be a few weeks, but we'll send an email out.
So the question was resources for parents in particular, authors that I trust. So one thing that's important to know is that for the most part, the behavioral interventions that we have to support kids really address the disruptive behaviors better than they do the attentive problems. So kids who are showing a lot of oppositionality, aggression, difficulty, kind of making it through the school day without getting in trouble, the authors I would recommend are Russell Barkley, Barkley, his name is Eley. You would hate that I don't know how to spell his name. A book that I would recommend for school-based interventions is by Linda Pfeiffer, Pfeiffer, and her book is all about ADHD, the complete and practical guide for classroom teachers, I think, something close to that. And it's actually very accessible, and it's short, it's thin, and it breaks down implementing behavioral reward systems and other interventions in the classroom setting specifically, and it talks a lot about how can teachers communicate more effectively with kids with ADHD, what can they do to set up their classroom to support kids with ADHD. So that's a great book from the classroom perspective. Another book I would recommend is called Incredible Years, especially for young kids. And this book is actually also paired with a program, a really fantastic parenting training program. And I actually think every parent should read this book, but it has some really great tips for how to manage behaviors and minimize destructive behaviors, recognize how you may be reinforcing some of those bad behaviors inadvertently, and how to kind of change the setup of your home.
What was the title of the last one?
Incredible Years by Carol Webster Stratton.
And she runs parenting groups too.
She does, yeah. There are a couple of different Incredible Years programs in Seattle. One is through Seattle Children's. I think there's another one on the east side. Is Carol located locally or? Oh,
She's what? She lives up on the hill there.
Carol is nearby. You go knock on her door.
Yes.
Okay, thank you, fascinating work. Do your, the differences you saw in regional brain rates, do those correlate to ADHD subtype?
No.
No, okay.
No.
Any thoughts? Any thought? I'm assuming you ran all those things and it came up.
Yeah, I mean, I haven't run it in our data because we don't have the numbers, but the studies that I showed you, they did not find any correlation. And again, I think it's because those subtypes are not actually all that valid.
Oh.
So when you have something that's unstable over the course of 8 years, it really interferes with the validity. I mean, some of those kids may meet criteria for inattentive 1 year because they only have 5 symptoms of hyperactivity. And so that's not really a valid way of parsing apart behavior, and unfortunately we just don't have a much better way of doing it. So I think they're just not very accurate descriptions of these kids. I think these kids are much more complicated than mostly inattentive or mostly hyperactive, and that's why we see change over the course of development.
And short follow-up, have you done any tests with any of your patients that are undergo remission? So you said like, what, 50% or something like that?
Yeah.
Diagnosed? Will it remit at some time? And what do you see in terms of normalization?
Yeah, again, so this is not my work, but the literature basically says that at least some of the symptoms will decrease after adolescence in about half the kids. And then the remaining people who persist into adulthood, it's variable in terms of which symptoms persist, but tends to be more inattentive rather than the hyperactive.
I work in the Seattle Public Schools, and I have parents who ask about drugs and ADHD. So, what should I say to them?
Illicit drugs or drugs for ADHD?
Illicit.
Yeah.
I was trying to be funny, but no, it's that kind of audience.
I mean, it's not funny because it's a real big risk for these kids.
Well, okay, I didn't know that there were illicit drugs on offer.
Oh, wait, so what do you, sorry, I misunderstood.
Pharmacological.
Oh, actual prescribed medication,
Yeah,
okay.
prescribed.
Different question.
Yeah.
Yeah, I know.
Well, let's have 2 questions.
I think it's a very personal decision for families whether to medicate their child. There's a fair amount of literature on what happens over time, and really there aren't any adverse outcomes that are clear to us. And actually, some of the research, this hasn't necessarily been replicated, only a couple of studies have been able to look at this. Some of the research actually supports the kids who get medicated, their brains look more like kids who never had ADHD by adulthood than kids who aren't medicated. At like very finite measurement, like for Purkinje cells specifically, they're looking at how the organization. And one reason for that could be that the medication actually changes the brain, but more likely, putting kids on medication allows them to engage with their environment in a way that is more normal, and the brain is very dependent on the environment and interactions with the environment in order to grow and develop normally. So imagine a child at school who is really checked out part of the time and missing clues both socially and academically. That child's brain is just not going to develop in the same way that a child who is able to attend to the lessons and attend to their peers' cues and make sense of that and have to learn how to deal with that.
Okay, yeah, sorry. Well, to follow, no,
We'll come back to it. You can go.
Sure, quite that.
I just have two quick questions. With ADHD, do you ever just see pure ADHD, or is there always some type of a comorbidity?
We do see it. Mm-hmm.
You have found pure just
Yeah.
ADHD?
Yeah. So I think the question is, is there anybody who has ADHD but no anxiety and no depression and no learning disabilities? Yeah. I mean, yeah, it's a good question. I think we do see it. I think it tends to be kids who have perhaps higher intelligence and they're able to kind of, well, not necessarily for the anxiety. Yeah, we do see it though. We do. Yeah, I think, there's a range of normal in kids in terms of how they express anxiety and depression, and even some oppositionality. And so the way that we would get to a point of actually diagnosing an additional disorder is if we thought it was above and beyond what we would expect a kid with ADHD to show in the first place. And maybe that's shifted over time, now that we're thinking about it more as a disorder of regulation more broadly. I tend to be a little bit more flexible in thinking about what I would expect from a child with ADHD in terms of those symptoms and behaviors.
And then the other question was, it seems like in what you read, that anxiety is so up in our teens, well, probably has to be, but especially in the teen population. And so with the ADHD population, have you seen that rise as well in the same parallel, or has it always been that issue?
Yeah, I don't know the answer to that question. It's a good one, and I don't want to guess because I really don't know.
I just didn't know.
Yeah.
If you had a child with ADHD, would you send them to a primary care physician, or would you send them to a psychologist? I mean, obviously a psychiatrist or a primary would be the one to give medication. But in terms of the actual assessment, who is the most qualified to provide that?
A psychologist, or maybe a pediatric psychiatrist.
Clinical psychologist?
Yeah, but a clinical psychologist would be most able to do that evaluation, or even a neuropsychologist.
Yeah, okay. It seems like when, so I have a couple different children, now some in college and one in 8th grader, but it just seems like when I have gone to primary care, it's just like a parent checklist.
Yeah.
And it hasn't felt
Yeah.
like that's an appropriate way to get all the information you need
Yeah.
to make a decision.
Yeah, I think, on the one hand, if you're strapped for resources and you need to get this kid some treatment quick, then I don't think there's anything wrong with going to your primary care physician, especially first, at least do those questionnaires as a screener.
Right.
But a more comprehensive evaluation is going to include getting information from the school, having a longer, these PCPs don't have enough time really to make you as much as they would like to.
Sure.
And then also screening for common comorbidities and addressing those as well is going to be harder for them. But I think once you've gotten that diagnosis, in terms of medication, prescriptions, you can go back to your PCP at that point, assuming you don't have, your child doesn't have a lot of medical complications. We generally refer our patients back to their primary care provider, and then we'll follow up or see them again if things get complicated or challenging.
Okay, thank you.
Do you see like a common correlation with kids with the ability to learn math and obtain math at all?
Yeah, kids with ADHD are in general at more risk for learning disorders across the board. The math disorder one is interesting. We haven't studied math disorder as much as we've studied reading disorder or dyslexia. But I will say that kids with ADHD tend to make more careless mistakes and careless errors in their math. And so even if they understand math at the like basic level, like get math concepts, they're still going to struggle with math because they tend to forget to carry the one, or do some of those, or their handwriting is messier and it's just harder for them to sort of keep track of what they're doing in the first place. But in general, you're going to see just higher levels of comorbidity.
Yeah, I work for a healthcare system here, and we've been getting a lot of requests coming around for neuropsych testing for ADHD, and we're not really sure what to do with that, because traditionally it's been more psych testing, and now it's been people requesting neuropsych testing.
Yeah.
Is this trending up that for a diagnosis for ADHD?
I love that it is. I think it's very important. And if they're 7 to 11 years old, you can send them on study. Again, it really depends on what the child is struggling with. But for the most part, I think it's very important to get a baseline. What is this child's general intelligence, and what are some of the cognitive abilities that, on the one hand, those cognitive profiles may not predict some of our more important outcomes, but they do predict where kids are going to have the most difficulty in school. And so that information does translate to recommendations for school. And I'm joking, but really, neuropsych evaluations can be thousands of dollars, and we pay our kids $40 to do it, and then we write up our report and we fill in with recommendations. And I actually think, from a clinical perspective, I really love doing evaluations and assessments because it really requires thinking about that. Well, this kid has this combination, this profile. What is that going to look like in school, and what kinds of supports could be helpful for him? So I don't know the answer to your question in terms, I think maybe there's more awareness that can be useful, and the schools sometimes require it in order to do a more comprehensive IEP. Maybe they're hopeful that the parents will go pay for it so the district doesn't have to. I think it's a good trend.
Is the word neuropsych?
Psych.
Neuro.
Neuropsychological.
Is there a space between neuro and?
It's all one word.
Are there resources, I noticed a lot of them are really working at like school age. What about when you get into like later adolescence into young adulthood, where maybe they didn't have the interventions of medication or behavioral interventions? Do you have any advice?
Yeah, that's a great question. For adolescents, I think get left out a lot. So there are programs like there's a TOPS group at Seattle Children's that focuses on, there's a middle school group and then a high school group, and it's really all around giving kids strategies to organize themselves, to plan, to do their homework, make sure they get their homework home and they get it back again, and it's like executive functioning coaching essentially. And so that TOPS group is great, but if you can find another group that does something similar, or even a tutor who will focus on executive coaching, that would, I think, tends to be the most important. I would also say at some point, you need to get it in writing that the school's been giving your child accommodations, so that when you go to take that, your child goes to take the SATs and moves on to college, those accommodations can follow him or her, because getting extra time on tests isn't just given to a kid in high school or college the way it can be in early elementary school. So that paper trail can be really important.
This might be a loaded question. I'm curious, you've mentioned early detection, and I think that there's been a push in the field in terms of early detection for everything, and it's good. What do you envision that looking like for infants with ADHD?
So the next part of our study is actually to look at very young kids who are at high risk for ADHD and see whether some of these brain correlates, and we kind of morph them to look like they should developmentally appropriately, whether those are going to be predictive of the diagnosis. And the reason that we're doing this work first is that, again, if we look at it from the bird's eye view and the group level, we might not find all of the markers at the brain level that are going to predict ADHD for all kids. So if we can find multiple markers for multiple subgroups and then try to figure out what that would look like in infancy or toddlerhood, then the hope is that kids, at least who are at high risk, could be screened or evaluated, and then we could do some potentially preventative or early interventions. The autism world has done a really fantastic job of looking at this. They've done sibling risk studies for decades now, and most of the findings that they've had that have been the most reliable have been at using EEG and at the brain level, and then eye tracking as well is another way to do it. But they were really, those clinicians, one of whom is a good friend of mine, really, she was convinced that a good clinician can spot autism in toddlerhood or infancy, and it's just not the case, and I think the same is going to be true for ADHD, so I don't think the effort's going to be necessarily on behavioral screening at that early age.
Thank you so much.
Yeah, this is fun, thank you.